my screen. Okay. All right. We have covered conservation of mass for control volume analysis. We already conclude the Newton's second law of motion. Today, we're going to look at the third one. We're still under second law of Newton, but today we're going to look at moment of momentum. Okay, moment of momentum. Okay, let's see what is moment of momentum. Okay, now before we start, throughout the lecture today, I want you to focus on only one concept, and this concept will derive or expand to a more lengthy equation. Before we start, you need to remember or recall what is meant by moment or the word torque. Okay, so let's say if you have a reference plane and there's a point there and you have a force. This is force, and the distance between this reference point A, there's a distance D, and the distance and the force is 90 degrees to each other and to the reference plane here at point A. The results of force times D or force cross D, we're going to look at vector cross product today. F times D, we will get moment. Moment or torque. Okay, so this action, force times D, the distance from a reference point, will give you moment or torque. What is the effect under this force? So this force is going to rotate. It's going to create a rotation effect. Okay. Rotation effect. This force is going to create a rotation effect. In this case, if you refer to force direction, you're going to have an anti-clockwise torque or moment referring to point A. This is the effect. So the red color is your input. Once your force and distance is perpendicular to a reference point, you're going to result a torque or moment action. Okay, memorize or remember this concept throughout this lecture. Later, we're going to keep repeating this concept by using mathematical model. Okay, later you will see a lot of very weird formula. However, we still contain this concept. Yeah, memorize this one, and then I hope you can memorize until the end of the lecture. So, but however, this is the concept that we'll be using for the rest of lecture today. Okay, so when you ask to what is moment, what is the torque, then recall force times D, you'll get torque. And remember the direction. Okay, direction of torque will follow the force. All right. We start. So I did explain how torque is just now. And we're going to input this torque or moment into our momentum equation that we learned previously. We're going to look at torque and angular momentum flow. Today we're going to learn a new word, torque and angular momentum flow. Angular, meaning you're going to see R, you're going to see theta, yeah. So you're going to see R and theta, where you're going to look at angular axis. So let's say this is your X, this is your Y, this is your Z. And there's a point there in the 3D dimension. Then you're going to refer to this location by r and theta to each of the axes here. So this is the theta. Huh? So each one will give you one theta. You have theta x, theta y, theta z according to axis or plane itself. So I'll give you more detail shortly. All right. Recall second Newton law of motion. F equal ma, which give you m v divided by t, because acceleration is velocity divided by time. So when you take mv divided by time, you get force. And we know that the combination of mv, mass time velocity, give you momentum. Okay, so this is what you learned previously. Today we're going to include the concept of torque, or F times D. Cross, we are using the cross product today. F cross D or F times D to get the torque. All right. Now you are very familiar with the equation at the bottom of your screen here. So this is what we learned previously. We have V times rho times volume divided by T will equal to your force. Okay. So because why? Because rho times volume, density times volume, you get mass. Mass times V, you get mv. mv is momentum. Momentum divided by time is the rate of change of your momentum equal to force. Huh? So how you read this mv divided by t is the rate, because you divided by t, we call it the rate of change of your linear momentum. Okay, it's quite a lengthy description, but you memorize this form, then you're able to understand the equation. Okay, so this one we already looked at this equation in our previous lecture. We put V times rho times velocity, volume, times volume equal to force. F equal to ma with second Newton law of motion. Now we combine what we learned 10 minutes ago. So this one is when we talk about torque, when we expand the equation later on, the velocity here, we talk about particle, 1 point. Particle means individual element, right? Particle velocity measured in the initial reference system, which is your global axis, which is your x, y, and z. X, y, and z. Which is this one, will always refer to x, y, and z. And this one will give you a vector form accordingly. So density and volume. Okay, so if you see this delta form here, it means very, very small. And this also will give you very, very small forces. So far we still at the mathematic model. So, and you're familiar with it. So let's take this equation a bit further. Okay, and force here, it means the resultant of forces under the effect of mass, velocity, and time, you get force. Okay, now we try to modify this second Newton law equation and try to link with torque just now. Okay, now recall 10 minutes ago I mentioned about moment, or torque equal to force times a distance, or we call it arm. This is your arm, or distance from a reference point at 90 degrees to the force, or we call it arm. So if you look at this equation, this is second Newton law that not yet developed to change to torque. But if you want to change this equation to torque, we have to do something on this equation. Okay, you agree, right? So how we going to change the left-hand side to a red color equation? We must add something to this side and this side. So the only thing that we can add is the arm to this equation. So both sides you times the arm, you will change this second Newton law to a torque equation or moment of momentum equation. So before that, you look at the diagram at the right hand side of your screen. This is the particle red color, and reference axis here is x, y, and z. And our origin is at the center here. And we measure from center to this red color particles is at the distance of r. And this particle is moving at the velocity of v. Okay, so there must be some force that make this particle move. Okay, and if you want to find or extract the energy of the motion that generate the motion, there must be some force that act on the particle itself. So we add one more element to your free body diagram here, which is your force. And what we learned 10 minutes ago, we define torque as force times arm. So if you look at this diagram, if you take this force cross or times this r, it's going to give you torque reaction or moment reaction. Okay, now back to the equation in yellow color here. So we're going to add r into the equation. So you are changing second Newton law into moment of momentum equation. All right. You doesn't change anything. You doesn't change anything in the dimension of the equation, but you just transform it by adding the arm of r or distance from the reference axis to the particle, which is r. So you're changing the equation to a moment equation. Okay, so the right hand side, if you take the F cross, okay, yeah, we are start looking at the cross product now. If you take R cross F, it's going to generate torque reaction, and the left hand side, because you want to balance the whole second Newton law, you have to add R at the left hand side also. So left hand side, you have additional R to your rate of change of your linear momentum that you see previously. Okay, now so far, no complex equation yet. You just add in the concept of torque to the second Newton law equation above. All right, the next one will be a mathematics concept that you learn in your advanced mathematics with this differential equation. So this is R that I explained just now. So I pull the equation up and recall your differential mathematics procedure, which is the differentiation equation. What happens if you have a differential on the left hand side? So we look at this component first. Okay, so you times the r inside because r is the constant value. So you can pull the cross product inside the bracket here. Okay, so you pull your r cross v rho change of volume into the equation, and let's look at in mathematical dimension what happened to this one, right? So you have d over t times r cross. This is cross, cross and the dot product here. So cross r cross velocity times density times volume. So this one you already know. If you take rho times volume, you get mass. Mass times volume, mass times velocity, you will get a parameter called momentum, mv. All right. So I'm going to extend this equation on your screen. So equal, if you do differentiation of, okay, let me erase my pen. It will be like you're doing a differentiation A cross B equation. This is the first part. This is the second part. Okay, so you're going to get dA, if you recall, equal to B plus A times dB something. Okay, so in this case you are dt, right? So you dt lah, and here also dt. Now this one is under differentiation chapter in your advanced mathematics lecture, so I'm going to let you do your own homework to understand the differentiation procedure. Okay, so we don't have time to explain how and the reason why you get this one. So basically is using the concept of differentiation. So the first part you get dr divided by dt cross. Okay, I will not use the word times or multiply because it's not the more proper one is a cross because we're dealing with a vector now. Okay, so there's a cross product times the velocity, density, volume plus r cross the differentiation of the second parameter, which is your momentum, divided by time. Okay, stop me. If anything look weird to you, stop me and ask me to explain to you if you don't understand. Okay. All right, let me clear my pen and move forward. All right, now if you look at the equation, this form, dr, the change of r distance divided by t, you know that if you change of length, how you calculate velocity? Velocity concept is you take distance divided by time, right? Distance divided by time. So same, in this case, r is a distance. This r is a distance. So if you take distance of r divided by t, you get velocity, v. Okay. So when you substitute this one with v, it become a v. You are seeing a cross product of v cross v. Okay, think back the vector cross product. If you have a velocity cross velocity, or you have a same parameter times same parameter, you're going to get 0. Okay. Now, if you don't understand why v cross v or a cross a, when you have two vector and there's a cross product of these two equals 0, go back to your mathematics teacher and ask why this one equal to 0. Right? We don't have time to explain on mathematics dimension. Go and ask your advanced mathematics teacher, okay, or lecturer. So the concept is, what is important is that you, when you have a cross product of a same vector, it will equal to 0. Okay. Now, since you see the dimension of this one equal to v cross v 0, so the whole thing, the first part equals 0. Okay, we will start cancelling and recalibrate or rewrite our equation now. Okay, so in this case, mathematics, we cancel the first term here. It will arrive at the equation that at your bottom. Okay, so what does it mean? It means that at the end, your d over dt, r cross v density and your volume on the left hand side here will equal to r times force. Why this one equal to force? If you look at this one, rho times density times volume, what do you get? Mass. Mass times velocity divided by time, what you get? You get force. F equal to ma. What is acceleration? Acceleration is velocity divided by time. So by looking at the mathematical form, this whole thing is false. Okay, so that's why on the right hand side, this one become false. Okay, look logic to you. Stop me. If anything on the screen that doesn't look logic to you, stop me and ask me question. Because all this will if you don't understand the procedure, later you'll be confused with the solution. You will be confused. Hey, why this one suddenly become positive? Why this one become negative? Or why should I convert to false and so on? So if anything that confusing, stop me and ask question. All right, we arrive at the equation at the bottom of your screen. I'm going to pull this equation to a new slides. Okay, we reduce the concept of torque equal to Ft F cross D or moment to this equation. And every time you're seeing this delta, which is a small changes, we are looking at particle dimension or individual particles. So this equation that you see on the screen is valid for individual particles in the system. Okay. However, when we learn about fluid mechanics, we will look at the overall system. So what will it change? If you have a collection of particles, okay, or we call it system. Okay, a system is a combination of all the particles together. We will use sum symbol. Okay, so mathematically, the above equation, you can modify into sum of your R cross F. Again, R cross F give you moment or torque. The left hand side also same, remain the same, only you need to know that when you look at the system, you need to integrate the individual component inside the system. You need to add an integration if you want to look at the whole system. Okay, try to understand the above equation. The above equation, you look at individual particles. So you want to look at the overall picture, you have to sum all the left-hand side component and right-hand side component. So right-hand side component is a differentiation equation. So you want to sum all the things on the left-hand side. You just need to use the integration. So you integrate the differentiation, you get back the total component on the left-hand side. Right-hand side, you just need to add the sum symbol to add all the forces you have. Okay, now so far we still at mathematics dimension. So I'm going to move forward. So this is just explanation. This is explanation of how you get transform from particles to system. All right. Now, as you can look on the screen here, the equation, we are looking at integration of something equal to the sum of something. When you look at integration and sum, remember this one is a system, meaning you look at the whole picture. Okay, the whole picture, not individual picture or collection of something. System. Okay. All right. Recall just now. I'm going to substitute the equation now. So just now we proved that your equation d over dt integrate of dt, you can pull your dt inside integration there. Okay, you can pull inside the equation. You become the left-hand side answer. All right. Now, what does it mean? It means that it's reversible between in mathematics dimension. When you pull your dt into the equation, it means that the integration is reversible. means you're able to change things back and forth. Okay, there's no changes in the system or in the parameter that you are analyzing. Okay, if you pull this one in and out, means you are assuming the entity that you analyze is interchangeable. Okay, right. This gives you, if you compare to the first equation and the last equation here, actually we're playing with the location of dt and either inside or outside. Okay, so we're actually modifying a little bit the equation. We pull this one out so that we can straight away differentiate the parameter r, v, rho dv. Okay, so as you can see from the screen here, something different from the previous lecture, which is the cross product. Previous lecture, we do not mention about the cross product. And still back to the concept that we mentioned 20 minutes ago, we are now looking at torque. What is torque? F cross D. So this is why the cross axis appeared in this equation. Yeah, this is a very important concept for today. Torque. I'm going to pull the equation up a little bit. Then on the left hand side is the rate. How you read the equation? Anything that we have d over dt means rate. This individual component is called rate. And here, integration of this whole thing, you know that this is your momentum, right? This is your momentum. How you know momentum? Just derive. Rho density times volume, you get mass. Mass, not dot lah. Mass. Mass times velocity, you get momentum. Momentum cross R, we call it moment of momentum. Okay, moment of momentum, because you take an arm, cross a momentum, it will become moment of momentum. Okay, this is how you read the equation. D over dt, we read as rate. And you look at the inside content, V rho volume. Volume times density, you get mass. Mass times velocity, you get momentum. R cross, R is an arm. When you take an arm, cross a component, in this case is momentum, we read as momentum of a moment of momentum. Right hand side is external torque. R cross F is our torque. External. Okay. Move forward. Next, I'm going to explain something that you learned many years ago in your advanced mathematics class. If you look at the diagram here, let's look at X, Y, and Z, and you're seeing there is a highlighted plane here. You're having a XY plane. I'm talking about 2D. 2D XY plane is the pink color, something like pink color in your screen. Okay, so this is a plane, and the force and arm is on the plane. Yeah, I slow it down. I repeat one more time. Your force and the arm, or we call it distance from origin to the force, on a 2D XY plane is going to generate a torque direction. Okay, this is a torque direction. So as you can see from the plane here, you know how to find the turning of your moment, right? I explained 20 minutes ago. You follow the direction of the force. Force times R or cross R give you a moment or torque. In this case, you follow the force and is anti-clockwise. All right. Now I want you to imagine something right now. You have your left hand and right hand, right? So now I want you to focus on your right hand. Right hand. Now I want you to okay, let me try to instruct you to do an action. So you focus on your right hand with your thumb pointing up. Okay, with your thumb pointing up and your four fingers. You close your four fingers. There's a direction of when you cross your finger, right? So as you can see here, your forefinger, when you close your four fingers, the four fingers will follow the F direction or the turning direction. And your thumb is pointing up. This is called right hand rules. We're going to use right hand rules in this session. Okay, right hand rules means we look at the force and the R here. You look at the force and the R. It's going to generate this red arrow here. This red arrow is your, okay, let me try to draw on the screen here. Okay. Now this is your thumb. All right, your thumb is pointing up. So this palm, your fingers, is going to follow the direction of your moment with F times R. So you curve in, all right? You curve in and your thumb is pointing up. So this direction tells you the direction of the torque forces. Okay, the torque forces going up. And the direction is under action of R cross F. Only happen when you have a cross product, then there is a direction of the cross product. In this case, we take out cross F will give you torque. This explain about this diagram. Try to understand how you get the arrow. I just explained about the right hand rule just now. Try to look at your screen. Try to relate the red color diagram and the left hand side diagram. Are you able to explain the T direction? If I flip my force to the another direction, what happened to the direction? Okay, now just a quick test whether to see whether you understand or not. So I'm going to draw a new diagram. You have your X, Y, and Z direction. Now I add in the force and the arm in the system. So what happened if you have arm R and the force is acting this direction? Is your force. Where is your T direction? Okay, where is T acting? Is it moving up or moving down? So if you refer to the right hand rules, okay, so first you look at your right hand and then you try to move your four fingers according to this diagram. So this diagram is this direction. This is your moment. So follow your four fingers. Your finger going to point down. Okay, meaning the torque direction is going to be going down. Under this section, the T is pointing down. Right? So far, I didn't hear any question. I assume you understand. All right. All right. Now, in this case, we assume the control. We'll start to bring back what we learned previously. We are now looking at control volume. So we assume control volume co-incline means is keep at the same dimension of your torque or of your system. All right, meaning let's say the solid line is your system. The yellow line is your system. And when you analyze the problems, you are having the analysis control volume same as your system. Red color is your control volume when you do analysis. So the torque will be identical. The torque inside this control volume will be identical in your analysis. What does it mean? The right hand side equation system you can write as control volume. You can change this one to control volume only when the yellow line and the red line at the same place, or we call it co-incline. Okay, I move forward. Okay, I already explained up to here. Then I'm going to explain one more time. We now look at fixed and non-deforming volume. You give you this equation. Left hand side is what we covered just now. Okay. Right hand side of the equation is what we discussed just now. R cross V density volume. Okay. So again, rho volume give you mass. Mass times velocity give you momentum. Momentum cross R give you the moment of momentum. Okay, the combination of this one give you moment of momentum. Sorry, this one is not moment, it's momentum. Momentum. So when you cross R, it gives you MOM, moment of momentum. And when you read the whole thing, dt is a rate of change of MOM, rate of MOM. Okay, and when you recall the Reynolds theorem, this famous name, Reynolds theorem always give you need to look at two dimensions, control volume and control surface. All right, so as you can see, if you compare, the structure will be the same like previous one. However, something changed in the content. Something changed in the content. Okay, so inside today you learn new equation. And this equation is moment of momentum equation, or MOM in short. MOM equation, right? MOM. So R cross V rho V are the volume, change of volume, and for the control volume, and dt. On the right hand side for control surfaces, we have R cross V rho V dot n hat dA. So you have a vector dimension here. So you need to deal with vector dimension also when you look at control surfaces. All right, I'm going to share a good news for this session. So, okay, all these are the one that we learned previously. I'm going to do something about this equation now. So this is a general equation for MOM. Okay, and for non-deforming fixed. So this one, if the question asks you to solve using moment of momentum equation, write this equation, you will score 1 marks for this equation. Okay. Right, move on. So all these, I will recall just now what we learned. You know that this is the individual momentum particles, not particle, moment of momentum in the system just now. System. And when your control volume co-incline with the yellow color boxes now. okay, red color is your control volume. Yellow is your system, means the system that you're analyzing. So when these two dimensions co-incline or at the same place, the torque is same. The torque is same for control volume and the system. Meaning you can change this one to CV. All right. Next, you look at the third equation on the screen with this one. So the Reynolds theorem that we see just now, Reynolds theorem gives you control volume dimension and control surface dimension. Now the good news is, okay, I highlight the red color on the screen here. As you can compare the above and below, the above is a general moment of momentum equation. The bottom one is from the Reynolds transport theorem, where look at CV and CS, and you compare left-hand side of both equation is the same. So we can equal these two boxes together. We can equal this, the first equation in the red box, equal to the second box here. We can pull these two together, put them equal. We get moment of momentum equation, and this one is useful when you solve problems. You write this equation, you score another 1 mark for moment of momentum equation. Okay, so this is useful when it comes to your test or final exam, when you need to analyze the control volume using momentum of or MOM equation or moment of momentum equation. Because this one, you will straight away lead you to the final answer. You look straight away, look at control volume, control surfaces equal to the force and the arm in the control volume. Okay, so this part refer to free body diagram or your sketch, your free body diagram. And left-hand side is all the parameter that in your control volume and control surfaces. All right, now there are lots of equations for today. So when we apply the MOM, there are a few assumptions where it's good news to you. First, we only consider flow happening in one dimension, which means when you solve MOM equation for this module, assume you have a uniform flow in your control surface or control volume. Okay, you are looking at 1D dimension. Number two, we always limit our calculation to a steady flow, or we will, as an average, we will assume the flow is steady. What I mean by steady? Always practice to draw your beautiful arrow for the control volume equal 0, right, steady flow there. You get another point for steady flow. So if you write this equation, 1 mark, write this arrow equals 0, steady, you get another mark. So by this combination, you score 2 marks out of 25. Okay. If you don't write, it means you miss these 2 marks. Okay. All right. So we are clear with how the assumption will help us in our calculation. We are now simplifying our analysis from MOM equation. First, we look at 1D. Second, 1D means you focus on individual direction. If you look at X, then the whole equation is in X. If you look at Y, then all your calculation in Y. If you look at Z, then you look at all your calculation will be focused on Z. All right. Second, always when you write this equation, automatically go and draw an arrow, write 0, write steady here, because we are assuming steady flow for our equation. Okay, these two are very important concept. The third one, we focus on the axis of rotation. What does it mean? I'm going to give you a diagram. This is a pipe with two outlets, a sprinkler system that we looked at previously. Okay, I think two more slides, then we stop for a short break. Yeah. So if you look at the diagram, a sprinkler system. So as you can see here, when you open the water, the sprinkler, the water will come out from both ends. It is your W. Okay, the W will spray out. And you can see that you have an omega here, omega W, which is the rate of rotation in radian per second, or sometimes give you in RPM, revolution per minute, if you omega. And you can see that there's a torque inside the system here. All right. Now, and then at the bottom here, you see the view from the side. The flow is from the bottom and then spray out from in the horizontal axis. And your control volume is actually in the 3D dimension. The red color or the pink color dashed line is your control volume. Left-hand side is a 3D diagram of the sprinkler system. As you can see, there's a straight line at the middle of the sprinkler that give you the theta and the z. So as you can see, we only look at forces that revolve at the axis of rotation. In this case is your z-axis. And you see what happened to the system based on z-axis. All right, so this is a third procedure when you solve MOM. Just take note on the second component in your equation here, which is control surfaces, because first component is 0 already, based on second assumption just now, because you assume steady flow in our MOM equation. Okay, so you left out with this one. So this one is not necessarily become 0 when you have a reaction where where most of the time your float will go across the control surfaces or your control volume, control surfaces here. Okay. All right. Let's look a bit more. Okay. So you can see I'm highlight something on the left hand corner with a red color circle there. Okay. I highlight the flow in and then section 1. So your flow is from below, go into your section 1, and it contribute to your 3D control volume there. Okay. If you look at the diagram in the middle, you have your R, your arm, to the volume, your volume. If you look at section 1, the red color is a 2D plane at section 1, which is here. Here. So if you enlarge this section to this diagram, the R and the volume of the water is going in along z-axis. That's why your V here is here. And in this chapter, we are looking at cross products. You take V cross R in this direction, it'll give you 0. When your velocity is perpendicular to your radius or to your control surfaces. Take note, when your volume, when your velocity is perpendicular to your reference area or reference plane, the cross product of your V times R will give you 0. Okay, this is a new things for today. Why this one becomes 0? Because you're looking at your velocity component, which is this one. Why is it pointing up? By looking at the diagram on the left, your input is from flow from below going to section 1. That's why your V is going up. Your radius is from, your R is from the center of the pipe, which is Z. And the velocity component is 90 degree to the plane in pink color here. So when your V is perpendicular to your reference plane, especially at the R, because your R is parallel on the surfaces, the cross product will be 0. Okay, have some capture this diagram for 5 seconds. Hold this diagram in your mind. I'm going to compare this diagram with this one. Do you see the differences with this one? This one, your force or all your velocity or forces, if it's along the plane, then you can calculate. Then there's a torque there when your force is on the plane. R is always on the plane. When your force also on the plane and there's a cross product, then you will get the T. However, if the component of this one is perpendicular, try to understand this important concept. If not, later you will confuse. Why this one 0? Why that one not? Not? Huh? So in this case, if the one that you're studying, you need to cross it with the R that on a plane. R will always stick to the plane or area, the flat area. And the velocity, if the velocity of forces is perpendicular to the area, it will give you no reaction. There's no torque or moment happening if the V vector is perpendicular to the area. Now, I draw another scenario. R, or maybe I use a different color. Then I'm going to stop the lecture for a while. So I draw R. Let's say you have another R. And you need to study another forces. And this forces velocity is on the surfaces with V. Then R cross V in green color, there is a value there, not 0, because this V is on the surface. However, if your V or magnitude of your forces is pointing perpendicular to the area, straight away it will give you no reaction. All right, this is an important concept. Listen back to this lecture if you don't understand this 0 concept. All right, then this one is the right hand rule that I just asked you to do just now. This is the right hand rules. So just now I teach you on the left hand side diagram where you identified the torque direction T just now. So it will be positive in anti-clockwise direction, or the direction of your finger bending direction. Anti-clockwise direction, because when you bend your forefinger, it's rotate anti-clockwise. Okay, and your thumb is pointing out. And then on the right hand side, when you open your finger like the diagram, okay, you know that your thumb is a cross product. So your cross product, you can see that the R and V is on the same plane. Okay, is on the same plane, meaning you can see that the R and V is at the same reference plane. So from here, you can calculate the V cross R. Will give you this one. Try to understand this concept, then you can do any question for this chapter. Okay, it must refer to the same plane. Anything that you cannot imagine with your right hand rules, then it becomes 0. Okay, I think I stop here. Then we continue. Let me stop recording.